welcome back. Let's do a shop talk, a final shop talk for 2020. This was an interesting year. It had its ups, its lows, and its devastating lows. So I'm keeping it kind of brief here. As you can see, I'm up in the new shop. This is not my basement. And you're not familiar with the machine next to me yet. This is a machine that I ordered something like mid-August just for my business, because I needed a reliable heavy-duty router for machining plastic and aluminium. I checked the work that I do with my CNC machining, and it's probably 75% plastic and a little bit of aluminium, and practically never I never get any work in steel to quote. So I'm not competing with the guy that has a Haas mini mill or a DMG CNC machining center in his garage. I need a reasonable priced machine that can do machining of plastic and soft metals on its own, and also can do sheet metal cutouts. I need a CNC router for sheet metal prototyping in a small scale, where laser cutting has too long of a turnaround time. I can show you two examples here. The first one, this is pre-hardened spring steel, 0.5 millimeter thick, and the other one here, this is 0.5 millimeter, I think, phosphorus bronze. And both were cut on my easel CNC router. Works perfectly fine, but I have now three routers. The easel, the Stepmore CNC fixed gantry, and this one. The Stepmore I took apart, and I want to do a full rebuild and make it just a precise machine, because it has its issues and they cut costs in a lot of places. But the reality is, when you run kind of a side business and have a day job, time to do projects like rebuilding a machine completely from scratch, that's problematic. So I decided to ditch the machine. I'm also going to sell the easel CNC router sooner or later, and I'm concentrating on this machine. This is a Sorotec Alu-Line 0605. 0605 is the travel. It's 600 by 500 millimeters, 200 millimeters in C. Doesn't reach all the way down to the table. Means I have 270 millimeters of clearance between the table and the underside of the gantry. It's a moving gantry. It's all aluminum. All axes have 20 millimeter linear rails and 16 millimeter ball screws. Rapids are, I think I set it to 10 meters per minute. The table is a 20 millimeter aluminum plate with a hole grid drilled and thread milled into it, M6 threads. I have some short clips about making the hole pattern in here. The first one shows the drilling with a 5 millimeter high-speed steel drill. I'm packing fairly often because I'm drilling dry here, and this is 5083 aluminium, which is fairly soft and tends to gum up the drill when you run it dry. After drilling, I took a single flute D-bit and I chamfered the top of the holes. Then I took a piece of carbide. I ground a single point, single lip thread mill on my tool and cutter grinder. And I used that to thread mill all the M6 threads, 110 of them. The program for doing the thread milling ran about something like 40 minutes, which is fairly quick. I could cut each thread in one pass, no spring pass, and it was a nice gauge fit with a go, no-go gauge. So that went super well. I have a tool probe on the table, and the spindle I have here is a 2 kilowatt Italian-made Techno motor spindle that goes up to 24,000 RPM. It has an external fan, so the fan is not connected to the actual spindle shaft means when I run it very slow, like 3000 RPM for drilling, I still have full cooling from the auxiliary fan up. This spindle has no HSK or BT or any other taper changer. It has a collet chuck, a ER25 collet chuck, with an excellent runout, by the way. On an end mill out here, like 40mm in front of the collet chuck with good Farion collets, I get like 3 to 5 micron runout on the end mill flutes, which is very good. But that means that I cannot preset the length of my tools. When I do a tool change, I need to re-establish my length of the tool. And for that I have the tool probe on here on the table. Means the machine starts with the first tool, does the cutting, and when the G-code prompts for a tool change, the C-axis moves up to G53 C0, means all the way up. Then you manually change the tool and hit and C start. Then the machine will automatically move over, check the tool length, calculate the offset from the last tool, and continue on with the exchange tool. So that way the manual tool change and possibility to run multiple tools is given. There is the same spindle is available with an HSK32 interface that is manually tightened and loosened with an Allen key. And I might buy that some point in the future, depending on how the whole machine works out. That would allow to use HSK taper tooling. And it's just a drop-in replacement for this spindle. So you take this off, put the other one on, and you're good to go. I didn't film any of the building. The machine came on a pallet in parts. I ordered the mechanics as a kit and all the electrics and electronics pre-assembled, tested, and ready to go. The controller is adding CNC. In a 4-axis configuration, I can hook up a 4th axis to this, and it runs via Ethernet on a Windows computer. I have some accessories that are not mounted yet. I have a Fogbuster MQL system, a minimum quantity lubrication that sprays ethanol or light cutting oil onto the tool. I have a dust shoe when I machine something like wood that goes over here, and a shop vac hooks up to it. The stepper motors that drive the machine are JLC closed loop steppers. Means it's a normal stepper motor, but it has an encoder on it, and the driver is also included in the package of the stepper motor. And when you run these steppers and they lose a step, for example, because you exceeded the maximum current of the driver, then it errors out. It stops, it dead stops, it stops the spindle, it e-stops. That means you're not running into the danger of losing steps and messing up your work because you overstrained your drives, which is a nice thing. Didn't go for servos because configuration of servo drives is not as trivial as it sounds, and I'm not going to go down that rabbit hole right now. So yeah, I built the whole machine, the mechanics, in about 2 weeks. I took my time. I didn't film a thing, and there was good reason for that. I needed some time, just myself and me in the shop. And I took photos, but I didn't film a thing. I needed just to work on my own. Want to put it together. It's now ready to go, except for an enclosure. It definitely needs an enclosure. I need a large housing. I'm going to build it out of an aluminum extrusion and Lexan, because high-speed spindle throws chips everywhere. And I have the tool and cutter grinder next to it, so an enclosure is given anyway. So yeah. You will see more about this machine. I will do a separate video on the machining, and you will probably see it in other videos too. Now that we have this thing here, this elephant out of the room, I have 2 other topics that might be of interest. The first one is kind of obscure. I found this in the NASA documentations. NASA, as a US government entity, has to release every paper that they produce for the public. And I found one on machining glass. When I read through it, it didn't sound too crazy. The requirements were fairly basic, a milling machine and some carbide tooling, and yeah, I tried it out, so I have a clip of that right now. This is a quick one. Did you know that you can machine glass? This is ordinary window glass with carbide tooling. I did not know that. I read about that in a NASA publication, and they state that a normal PCB carbide drill will drill regular window glass. In the publication, they state to bed the glass in wax, so the back side doesn't blow out. But for entertainment purposes, I'm not willing to go through the trouble of melting wax and bed the glass in it. I just clamped it down onto a sacrificial piece of aluminium, and we're going to drill it. We're not center punching it, we're drilling it directly. So carbide drill running at 1000 RPM, and I'm using cutting oil. They especially state to use cutting fluid to keep the cut cool, otherwise you get thermal shock and it blows up. They use tap magic in the publication. I'm using ordinary cutting oil. Okay, I think we still blew out the backside. If you saw, this works. I'm not going to unclamp it right away because I want to try milling too. So that's the carbide drill I used. Regular, cheap, $3 carbide drill, PCB drill. The cutting edge is still intact. It shows some signs of wear, but it's not terrible. I guess that's what you get when you drill glass. I drilled with a 1.7mm drill, and this is a 1.7mm drill shank, and this is a close, tight fit. So that's quite nice. Let's try milling this stuff. Okay, that's a 2mm 3-flute PCB end mill solid carbide, and we're just going to try to mill some glass with it. I'm running at 1000 RPM again, and I'm going to take like 50 micron stepped increments. I'm just going to move it. I'm plunging down from the outside, cut a slot, return, go deeper, and work my way down that way. This works way better than I would have expected. I increased my depth of cut to 200 micron on the last cut because it went that well. I will cut a little bit deeper, but I will increase my speed, spindle RPM that is. to 3000 RPM. Let's see if we can break this glass. Okay, the higher speed and feed creates some minor cracks in here, so we better drop down. Until now we basically did face milling, we just dropped down incrementally. Let's try stepping over to the side and do side milling. I suspect this will not work too well. Even side milling works way better than I would have expected. I stepped over 0.2 millimeters at 200 microns and at a depth of 1.6 millimeters, and it's just cutting nicely. I'm not entirely sure if it's really more like grinding or cutting, but it's removing material and the end mill doesn't seem too angry about it. The paper from NASA claims to pre-drill when you want to cut a pocket inside of a part. Let's try it without without pre-drilling. Let's cut a pocket here, or at least a slot in the center of the part. I will move the x-axis and at the same time plunge down, so I'm doing a ramping cut. I think I cut a slot that's 1 millimeter deep. Hard to tell under the cutting oil. And yes, I'm very aware of the dangers of glass dust, silica dust, but as we're cutting completely under cutting oil, I'm not worried. And we're using a relatively low spindle speed. So yeah, that's a slot in good old glass. Let's look at it. This is the 1.7 millimeter hole. The underside blew out. Just clamping it down to the piece of aluminium did not the trick against blowout. But as you can see, this is a darn tight fit on a 1.7 millimeter drill. You could do some precision machining here, but the problem is when you combine glass with steel, you might get into trouble. And you don't want to do any press fitting glass, I guess. Here's the pocket from the outside we cut. The side walls look nice, the floor looks nice, only the upper edge here is a little bit chipped. And here's the slot cut into the glass. Same story here, floor and side walls look nice, but the edge on top looks a bit ragged. Could be speeds and feed, could be the tool I was using, the cutting fluid, whatever, heat input, just the nature of glass, I'm not sure. But yeah, it works. You can machine glass here. You also have the option to surface grind glass, cut it on the tool and cutter grinder. You can do a lot with usual shop tools in glass. And when you're doing prototyping or instrument making, there are times when you have to cut and grind glass in a machine shop. At my day job, I had to cut and surface grind glass and also ceramics. That's just the nature of the thing when you do prototyping or test equipment. And yes, this is real glass. I'm not going to break it for you on camera. Don't want glass shards all over my shop. This is the end mill under severe magnification. And we have a 3-fluting end mill and 2mm diameter. Here is one cutting edge. Here, over here, and here. And if I get this in focus, you can see that it's chipped. It's not a happy end mill anymore. My guess, which is really only a guess, that it chipped during the plunging. The plunging didn't sound too nice, but overall it doesn't look terrible. It's a well-used end mill that has milled glass. The drill on the other hand, this is the drill. Standard PCB 2-flute drill with a 4-facet grind, and you can see the cutting edge of the main cutting edge on the corner here, and that doesn't look too shabby. It's not chipped. It has some abrasive wear, you can tell that by the light reflection on this edge here. That's the cutting edge. There is a light reflection. If there is a light reflection, you have a corner round over. The corner round over usually is either microfracturing of the carbide or abrasive wear. And in the case of glass, I would think it's abrasive wear. So that's a quick autopsy of the tool. The tip, the center, is still in good nick. What I would expect after a few holes in glass with a PCB drill, that the OD of the drill changes. That the spiral OD of the drill gets abraded down. That's something I would expect. But apart from that, even as we blew through the glass, it didn't hurt the drill. That's quite impressive for such a cheap tool. So yeah, that's machining glass. Not the usual thing that you see every day, especially with a cutting tool and not a grinding tool. But I also have something on the humble blowgun, air gun, that you need to clean off machines and fixtures. As many of you know, I do a lot of very small work, small diameter bores and stuff like that. And a standard blowgun is just too big for most applications. So I 3D printed a nice adapter for that purpose, and I'm going to show it to you here. By the time it might be known that I do really a lot of small parts, and small parts usually have small bores, and a lot of them are blind bores. To get the chips out of those bores, that's always a little bit of a problem. When you use a regular air gun or blowgun, you don't get the chips out. Usually I resort to flushing them out with isopropyl alcohol in a needle bottle like this. That works quite well, but it uses quite a bit of isopropyl alcohol. And these days the stuff gets rather expensive. The alternative is of course compressed air, but air guns don't have a nozzle small enough. I could machine just an adapter and solder in a capillary tube, but where's the fun then? So my idea was to use Luer Lock tips. Luer Lock is a standard. It has a taper and a 2-star thread on the OD, and this is used all over the place in medical, chemical, laboratory equipment to connect small diameter pipes, to mount dispensing tips. These are solder paste dispensing tips, syringe tips, stuff like that. It's just a very universal connector. You can use them only with the taper. This is almost like a Morse taper. It goes on and holds only by friction. But I wouldn't dare to do this with an air gun, because this looks like a nice dart that would embed in your leg. That could hurt. So for those purposes, you have the two-star thread on the OD of the Luer Lock, and this gives a positive registration and cannot fly off. The problem, you can buy fittings, adapters, male, female, Luer Lock in plastic, stainless, whatever. Or you can 3D print one. I found a model of a Luer Lock on Grabcad. This was a Luer Lock to 1/4" MPT thread, something like that. And I pulled the model in CAD and I just cut away all the threading and modified the end so it presses on the tip of an air gun. And the other end, the print is fine enough. I printed this in PLA with 0.1mm layer height, and this is good enough so the Luer Lock tip screws actually in there. It's a little bit tight, but that's good. And here you can see that the taper, the central taper goes into the tip, and the Luer Lock itself screws into the two-star thread. This is a very positive registration. We have different style of tips. We have these like dispensing for solder paste. We have stainless steel blunt needles. There are also sharp syringe needles that will penetrate your skin and hurt. And there's also plastic ones. I think I like these the most for what I want to do because they don't scratch the part. These are nice and robust, but they will scratch the part if I'm working with something else than hardened steel. So, and these just don't go far enough into a bore. A friend of mine gave me a set, a sample kit of these Luer Lock tips. You can buy them on AliExpress, eBay, or on solder paste places or laboratory equipment. They're not that expensive and nice to have around. They also fit on the end of a Loctite bottle, by the way. Small and big tubes. And you can buy bottles like these that also have a Luer Lock taper. These have only the taper, not the lock, but you don't exceed as much pressure with these. I'm dedicating one of my air guns for this purpose. I'm going to cut the end here so it's not as long, just with a regular pipe cutter. There we go. Okay. Blew out the chips, and now we can press this end piece here on. This is a very tight fit, which is good. There we go. And then we can screw in a tip. And we have our precision air gun with Luer Lock connector. The question now is if this will withstand the full 6 bar of pressure on my airline. It most likely will do, but I don't want any chances of this going ballistic. So I'm going to set this up on the mill, and we'll put in a cross pin, tangential to the diameter of this aluminium tube. 2 cross pins, maybe a 1 or 2 millimeter pin, and that will positively hold it in place. Back from the mill, I put in 2 1.5 millimeter dowel pins, and I put the holes through with a 1.5 millimeter end mill, cutting a notch into the aluminium tube and cutting 2 holes into the PLA Luer Lock adapter here. So this is a definite positive registration. For now, something to happen, the PLA has to fail. Time will show. So still be careful. Here we have a look at the 3D model that I got off Grabcad. I will supply a link down in the description. And here you can see the 2-star thread where the Luer Lock taper can screw in. And now I need to modify this model for my purposes. First, we cut off all the excess on the back with an extrusion, just cutting away. This is not the most elegant way of 3D modeling, but it does the trick. Adding a cylinder with an ID slightly bigger than the OD of the blowgun. Another cut to remove the hex in front. And that gives us our basic geometry. And then we just add a chamfer on the inside here. So that's the part that we need to 3D print. And here is the link to the Grabcad model that I used. He provided the Luer Lock tip with different threads, but Grabcad models are licensed for free to use for non-profit, so I cannot re-upload the modified model. So if you want to make something like this, you have to make it yourself. So yeah, that's the Luer adapter. This video was planned for end of 2020, but life happened and I didn't have time and the right mood to do video editing, so you're getting it now in early 2021. Doesn't change much, but here we are. I wish all of you a good year 2021. Hopefully it's getting better, slightly better than last year, but we will see. Thank you all for watching. Thanks for the ongoing support. It really means a lot to me. I hope you still enjoy the content I put out. I hope to get back to a regular schedule soon. At least one video per month, hopefully 2. Thank you all for watching, and I'll be back.